Proud to introduce Dr. Alberto Malinverno from the Lamont-Daughtry Earth Observatory in Columbia University. Dr. Malinverno has done a lot of work over his incredible career in marine geology, starting off there, and now transitioning to some more astrobiology related topics regarding sediment cycles and lunar distance, length of day. All right.
Thank you. Thanks to all, and Lisa kindly sent me an invitation, but I have to say I'm not an astrobiologist. I'm an amateur astrobiologist, maybe, but I'm glad that astrobiology is a truly vast subject because I think we can get this in. Okay. So I'm from the Lamont-Daughtry Earth Observatory. This year is our 75th. But I'm also highlighting in this slide the funding organization. Simons Foundation is funding this work. And the project that I'm in involves a lot of other people. This is the Cyclo-Astro project. And this is the very crowded slide about all the projects that are being supported by Simons and all the people who are involved. There's 5 projects plus a cyclo cohort program, which takes care of all the early career students and early career scientists that are involved. And I'm in project number 1, empirical Earth, Moon, and Solar System parameters. And here's my collaborators that I absolutely need to acknowledge. Stephen Myers at the University of Wisconsin, who's been working with astrochronology and cyclostratigraphy for a long while. Linda Hinoff, even more so. She was the instrumental force in coordinating this big project with the foundation. Yujing is from Peking University, and she came as a graduate student at Lamont as a visiting graduate student, and she did an amazing amount of work. She's been fantastic to work with, and we'll get back to what she has done for this project in the course of the presentation. So, as some of you, I'm sure, know, we have many examples now of astronomical cycles recorded in sediment. So here are some pictures from the Miocene and Pliocene, so the period between 23 and 2.6 million years ago. And the top 2 pictures here are from Sicily, these are from Spain, and you see this amazing cyclicity in the sediments. And so it's been suspected for a long time that these were astronomically related. So here we see one of the fathers of North American geology, Carl Gilbert, who in 1895 wrote this fantastic paper that I encourage anybody who's interested in the subject to look at. Sedimentary measurement of Cretaceous time. So he refers to these Niobrara group rocks from Kansas in this case. And if you read that, it's the purpose of the paper to describe these regular alternations and correlate these with an astronomical cycle of known period and deduce from this correlation an estimate in years of a portion of Cretaceous time. So he has basically written up the program of astrochronology, and he correctly identified climatic precession cycles in this data set. It's an amazing. So the idea has been around a while and now has been substantiated by much research. This is one of my collaborators, Stephen Myers, and this was a commentary to another paper that worked on rhythmic stratigraphy. But the interesting analogy he makes, and again, I think it's pertinent to the astronomy side, is that the space telescopes are really looking into the past of the universe by looking at farther objects that are farther and farther away in space, and therefore the images that we see are farther and farther back in time. But what about our own solar system? How can we go back in time there? There's no telescope to do that. But the argument they make is that this rhythmic stratigraphy could be the observatory. It could be the only observatory that we really have. Okay, and so that's the spirit of this work. So going from astronomy to geology, We see that intersection, that Venn diagram. And astronomy has given this tremendous contribution to geology with astrochronology, with the ability to date sedimentary sequences by identifying cycles that correlate to astronomical cycles of known period. And that's the discipline of astrochronology. And now a lot of the geological timescale is in fact constrained by astrochronology. But what about going the other way? Can geology inform astronomy in some way? Can we go back in time and say something about what was happening in the solar system, in the Earth-Moon system, in deep time, essentially? And so that's again the subject. So we can go to the fundamentals of these. And so these are the astronomical frequencies that we'll talk about. So some frequencies G are frequencies of precession of the perihelia of the orbits. And so you can see them illustrated now as the orbits are precessing, right? You see the outer one, the red one, which is Mars. And then there's frequency of precession of the ascending nodes, which essentially are the frequency at which the planes themselves oscillate compared to a reference plane for the solar system. Another very important frequency is that of precession of the Earth's spin axis. How often does the Earth's spin axis go around? And right now, to do a complete spin takes 26,000 years, okay, that you see there. The important thing is that, and I'm going to go over this multiple times, that if you look at the basic equation that controls the frequency of precession, the axial precession, it depends on the distance between the Earth and the Moon and on the Earth spin rate of the Earth. Okay. And so these are the cycles in the Earth's orbit and in the spin axis orientation that are important to control Earth's climate and consequently the deposition of different kinds of sediment. So the chain of reasoning that you see at the bottom of the slide simply says there are these astronomical cycles. They affect the amount of solar radiation that reaches the surface of the Earth, different places, which changes the climate. The climate changes also affect the kind of sediment that is deposited. For example, if you have a more rainy, more humid climate, you may deposit more products of the erosion of pre-existing rocks, those are called clastic sediments. If instead you have a more dry environment, maybe all that gets deposited are microscopic shells of foraminifera and similar organisms. So you have a more calcareous deposition and so on. So these depend on combinations of these frequencies. So the changes in the Earth's eccentricity depend on differences between the G terms, the periods of changes in obliquity, which controls the seasonality, how much is the difference between summer and winter, depend on the S frequencies plus the frequency of axial precession. And the figure here shows the axial precession frequency. But in fact, what we record in sediments is called the climatic precession, and that depends on the sum of K and the G terms. So this is a very simple illustration of what you see in these series. So the top cycles marked as GI minus GJ are these packets every 100,000 years. And these are the climatic precession cycles. So these alternations between the harder rocks that show up in lighter colors and which are, I think in this case, are more rich in calcium carbonate, which makes them stiff, compared to the darker ones, which instead are more rich in clay, which makes them softer. These are precession cycles of climatic precession. So they have a slightly different frequency from K, is G plus K. And these are arranged in bundles of 100 kiloyears. And they themselves are arranged in multiple bundles that cover 400,000 kiloyears. So these are called the long eccentricity cycles, short eccentricity cycles, and precession cycles. So we can see all of these in the sediments, but these sediments have different ages. Unfortunately, I could never, somebody gave me this picture, but they never told me where it comes from. I think it comes from a beach in northern Spain. Sopelana, right? It's the Sopelana of a famous outcrop, a spectacular outcrop of almost vertical layers, so you can walk along the beach and see all these sequences exposed and measure it and analyze the results. So this is just to, again, stress the precession frequency part, because we're going to focus on that. So the attraction of sun, moon, and planets on the Earth is an oblate ellipsoid, right? Has a tilt on the orbital plane where these forces are mostly directed. And so those forces are trying to right the Earth, but of course, the Earth is a rotating object. So instead of that, you get a precession. Just like a spinning top, if I were, I should probably, when I give one of these talks, get one of those spinning tops, and you will see the top spins at a very high rate, but the axis of the top also takes a much slower spin. That's precession. So any inhomogeneity, right, in the top will do that, and the Earth is squashed at the poles, so that's enough of it, and so you will have that precession. So here's the simplified equation where we are comparing the value of K with respect to a reference value. Depends on the Earth spin rate and the Earth moon distance here. And so again, it's important because it controls the frequencies of climatic precession and obliquity, which may be recorded in these sediment cycles. And why does it change with time? It's an effect of the tides. So here we see what's called the equilibrium tide, the simplest way you can represent the ocean tide, which dominates this part of the signal. So if you have no friction, the Earth is spinning this way viewed from the North Pole, the moon is going around the same way, everything counterclockwise. You would have the two tides on the two sides, right? But because there's some friction, and because the Earth is spinning much faster than the moon is going around, if you put some friction in the system, then those bulges get slightly pushed. And this induces, first of all, this dissipates some energy, ultimately as heat, in the system, and so slows down the Earth's rotation. But because this mass here, this bulge, is closer to the moon than that bulge, it also tends to accelerate the moon in its orbit, pushes up to a higher orbit. And so the two effects of tidal friction and tidal dissipation are that the Earth spin gets slower with time, and the moon moves farther away with time. And the angular momentum of the Earth-Moon system is conserved. So the combination of angular momentum due to the Earth spinning and the moon going around is conserved, is the same. But the actual kinetic and potential energy is actually, some of it goes away into heat. The consequence of that, if you go back to that equation, is that the precession frequency should decrease with time. It gets slower and slower as time goes on. Yes, I think that's all I wanted to say here. So, okay, so we have all of these parameters, right? If you think of it. So if we make a complete list, we have the G frequencies, the S frequencies. There's about 5 of them that are important for the effect on the Earth. We have the precession frequency, and we have the sedimentation rate. And then we're going to have a data vector of data that contains the properties, sedimentary properties measured in stratigraphic depth. Okay. A key parameter is the sedimentation rate. So if we take a piece of deposited sediment and we look at the cycles with some measure of physical property, right? If you look at the cycles in that property, if the sedimentation rate was constant, then we can, and we knew it, we could translate depth to time, right? So that's a key property. So we clearly need that. We can then apply a Bayesian type of approach. And so we will have a prior distribution, a prior probability density function for all of these parameters, which could be determined by modeling results and associated uncertainties. So, and we'll see an example, I think, in the next slide on how we can set that up. And so this does not come from the sediment data, okay? It comes from somewhere else. It's another source of information. We can establish what's called in the local jargon a likelihood function, which is based on the difference between data predicted by these frequencies and by the sedimentation rate and the data that we observe. The bigger those differences are, the lower the likelihood, right? If we had a perfect fit, we would have the super maximum likelihood. Never happens, not to worry about that. In fact, as we'll see, we're really looking for signals that are generally weak in a lot of geological noise. That's what this is. Now, in the Bayesian formulation, you can define a posterior PDF, which quantifies the final uncertainty in these parameters and combines by multiplying the prior and the likelihood with this normalizing constant. It combines information from all other sources that were not the sediment data and the information in the sediment data. And so that represents our final state of knowledge, if you will. That's how well we can determine this. And we can assign uncertainties to everything. So that's a key point. We just don't want to have the best fit solution, which may be very hard to do, but we also want to have how good is that solution that we got? How well do the data constrain the answer? Okay, so these are some results of long-term numerical integrations and modeling, the tidal modeling on a global scale. The Gs, the 5 Gs here, and the 5 S frequencies here are from these long-term numerical integrations of the solar system. So basically, they start the solar system at the present state, as well determined as we can make it, and then go back in time. So turn the time the other way. This is work from all of this is work from the group of Jacques Laskar at the Paris Observatory. And then see how these frequencies evolve with time. So they basically let the planets go, and they do a spectral analysis to determine the G and the S frequency. They also repeat this work many, many times by varying the initial conditions just by a little bit within the uncertainty that we have about the initial conditions. And so you get a slightly different evolution of the system. Now, some of you may know the solar system is a chaotic system, but these frequencies themselves tend to be relatively stable. Okay. So trajectories start to differ about 50 million years if you move either in the future or in the past from the present state. But as far as the frequencies themselves of oscillation of the perihelia and of the orbital planes, those remain relatively stable. So what I'm showing to you here on the horizontal axis is time going to the past in billions of years. So we're here at 3.3 billion years. We just chose that. That's about as far back as we think we can get good sedimentary data anyway. And you see these images. If you were to take a vertical cut, it would represent the distribution of values of G1, let's say 1 billion years ago, with this in these experiments. So you can see that they do spread out from the present value. But the important thing, you see these bars, those are measuring how big the change is in terms of the present value. So G1, which is mostly dominated by Mercury, changes by a few percent. G2 is mostly Venus, 0.4%, and so on. So you can see that these are very small. Once you get to the outer planets, they're really small because they're massive and these frequencies change very little. So the G and the S frequencies remain nearly constant, but K instead, if you go forward in time, you see this substantial change. Okay, so this little tiny bar now is 50% of the present value. So you can see that it has changed tremendously with time. And so that's why we're going to concentrate on that. So we're going to assume that the G's and the S's for now, we keep them constant to whatever value comes out of here at the particular time that we're looking at, but we let K instead be a variable and try to see if we can determine it from the data. Yes?
Remind us what K is.
K is the frequency of axial precession. Is 1 over the time it takes for the Earth's axis to do a full turn with respect to the fixed stars, right? Yes. Yeah, sorry. Thank you. I should say, please remind me if I start talking in single letters. Yes, that's what those are. But the two single letters that are important here are U, which is the symbol I use for sedimentation rate, and K, the symbol I use for axial precession frequency. So I'm going to show you an example, which we analyzed and published, in fact, in 2018. So it comes from this Shamalin formation. It's a Mesoproterozoic formation in China. They did an XRF analysis, and we're going to use these time series of the ratio of copper to aluminum, which is the one that seems most sensitive to, again, the difference between different kinds of deposition here. And I'm going to show you the fit to the data for different tracks. So I mentioned that we have a notion of a predicted data. And so in this case, the predicted data is the fitted sum of 15 sinusoidal functions with frequency of eccentricity, obliquity, and climatic precession given by all the parameters. Now, in our case, we will keep G and R as fixed, but K and U will be variable. So axial precession and sedimentation rate. So here we have started with an initial guess to the sedimentation rate, and the value of K of the precession frequency is the present day value. So today it varies by 51 seconds, arc seconds every year. And so you see that now we have fitted those, and you see that there's some fit to the data. The red is the fitted curve, the black is the actual data. But the fit is not that great. If you were to look at the R squared of the fit, is kind of low. The maximum R squared would be 1 if it was a perfect fit. And down here in this plot, I'm showing you the periodogram, which is a really crude estimate of the power spectrum of this data. So where you see peak, there should be periodic components. And what you see here is the predicted frequencies for eccentricity, obliquity, and climatic precession. You see, there's not a terribly good match between the data themselves and between peaks in the periodogram and where you think there should be astronomical signal. So the data fit is poor. Now, the first thing that we can do is to change the sedimentation rate. If we change the sedimentation rate, all of these peaks, all of these predicted frequencies move here because we have changed basically the depth to time translation. Now the eccentricity frequencies at least have to some reasonable fit in here. They're catching some peaks. But there's a major spectral peak here that is completely, does not correspond to any astronomical cycle, so we're not accounting for it. And so the data fit is still not very good. The second thing that we can do is change the value of the axial precession frequency. If we do that, that doesn't do anything to the eccentricity cycles. They stay where they were because they don't depend on K. But they move, in this case, I increase the K. they move this predicted frequency all the way up to higher frequency. And now we're catching that big peak. We're catching something here that may be associated with obliquity. And so now we have the best fit. Now you can see that the predicted data do indeed start to resemble the real data. They have the right cycles, they have the right kind of modulation, right? So this is a characteristic of this data, that the amplitude of the precession, which is given by these high frequencies, is modulated by eccentricity. Okay. And so now we got the best fit. So we could take this, go home and say, okay, we got the answer, right? But we really want the uncertainty. And so instead of just getting the best fit, this is really to show, this is not what we do, okay? But it's really to show you what the basic idea is to adjust all of those frequencies on the basis of changing U, the sedimentation rate, and K, so that we get a good fit between predictions from the astronomical model and the measured data. But we really want to calculate a PDF. We want the uncertainty. So what we did here was, there's precession frequency varying between, in the interval where we see the best fit, between 82 and 94 arc-seconds per year. The sedimentation rate varies around what we find is the best fit. This is the logarithm of the posterior. The reason that this is plotted here is that you really see the structure, the general structure of this PDF. But then we plot the posterior itself, and so you see it's actually a single peak. Okay. Then we can simply integrate this PDF on the two axes. We get what are called marginal posteriors for the sedimentation rate and for the axial precession frequency. And so now we have the uncertainties. So the maximum a posteriori is the highest value for the posterior. This is the mean of these PDF. The two are closed because they are pretty symmetric distributions. And the blue line here shows you the prior distribution. So in this case, we had a very vague prior for the precession frequency, and we had a uniform prior for you. So we were basically saying we don't know what the sedimentation rate is. Any value is just as good as any other a priori, within some bounds. Okay. Bounds on sedimentation rate for the geologists in the audience, we can set on the basis of paleoenvironmental consideration. Maybe there's some biostratigraphy around here, not in the Proterozoic, but there's some radioisotopic dating higher up in the section. In a segment, there's two radioisotopic dates in a part of the section that has a similar lithology than the one where we have the high resolution XRF. So we have some idea about the sedimentation rate. It's not that we have completely uninformed. And of course, for data that are more recent than the Proterozoic, we will have better constraints to set up a prior, again, with a maximum and a minimum at least. So again, values of the G and S frequencies are expected to vary only a little bit, so we have them fixed to their prior mean. We also developed the Monte Carlo method that now goes full glory and actually gets the posterior PDF for everything. Right? I'm not going to show that here, I don't want to scare you. But the short stories for this data set, the answer is very similar to the one we got here. In other words, allowing for the G and S frequency to vary within the bounds that are given by the modeling doesn't really make much difference to the estimate of either sedimentation rate or axial precession frequency. One thing that I want to also stress is that we are careful with the significance of the statistical significance, if you will, of this data. Because if you give yourself enough freedom, geological signals are from a time series analysis point of view, are like a kind of red noise. So, has more power at low frequencies and less power. So they're these rich, wiggly things with a lot of oscillations. So there is a chance that we may just be fitting geological noise. Noise from the point of view, of course, of astronomical cycles. I mean, it has lots of geological significance, but not related to astronomical cycles. So how do we know that we're not doing that? Okay, it's always a question, and it's been one of the big criticisms to the use of this indiscriminate use, if you will, of astronomy, finding astronomical cycles. So the way we assess that, we basically repeat the procedure that I showed you earlier. A large number of times, in this example, 1,000 times. But instead of using the real data, we make up some data that have the same kind of spectral, broadband spectral characteristics as the real data, but they have no astronomical cycles. And then we ask the question, how many times out of that 1,000 random time series would we find with this method astronomical cycles that give you a fit as good as the one we got from the real data? Okay, so if that happens often, right? If you get 30% of the time, let's say, you can get the same fit we got from noise, then you would say maybe this is not such a great data set, right? If instead it's very uncommon to get that, then you would say that's significant. Okay, and so formally, there's this definition of a p-value. We may have heard of this and so on and so forth. But basically what we say is how many times out of 1,000 did we get a data set that fitted that? In this case, we got 1 out of 1,000. Okay, so p is 0.001. And so we would say, okay, you will never, probably will never get the case where you never, ever, ever get that chance, but this seems a pretty low chance. We'll take this one to be good. Okay, but it's important to do something like this. Okay, I want to stress that. Because again, you know, if you're not careful, you may be overinterpreting some kind of random variation as real astronomical cycles. Okay, so what do we do with this? Okay, now, so I'm sure that most of you are not that thrilled about the axial precession frequency, but what does that mean? Okay, now, how do we get length of day and lunar distance 1.4 billion years ago? We can get that now. So if you look at that equation there, right, it's the same that I was showing you, the simplified version of the precession equation. So you really have measured that, one parameter, but you're really interested in two. Length of day is 1 over the spin rate, right? And that's the Earth-Moon distance 1.4 billion years ago. So you cannot get two numbers out of one, okay? In fact, if you plot now this ratio of the Earth spin rate to the present to the lunar distance ratio here, if you have some value of the axial precession frequency, you basically have to be on that line. Right? So you have one number, and when the number is saying, okay, in this space, you have to be on this, you have to be on this line for that value of the axial precession frequency K. So you need one more constraint if you want to know. And that is ideally provided by the conservation of angular momentum. So what you see here is if you spin the Earth faster, you have to have the moon farther away to maintain the same precession frequency. Luckily, with angular momentum, it's the other way around. If you spin the Earth faster, right, the moon has to be closer to keep the same angular momentum. The present values here where both of these ratios are 1. And so that's what the picture looks like. So the conservation of angular momentum gives us another one of these relationships. And when the two intersect, that's it, you have your answer. So this is the value of the Earth was spinning about 30% faster, and the moon was about 88% the present distance. So it was closer to us. And again, now the conservation of angular momentum is this line, and of course goes through the present value. Sorry, didn't want to go back. We can also get an uncertainty on this. Of course, we want to have an uncertainty. And basically, we define the uncertainty. This is the uncertainty around the thin line, define the uncertainty. This is a blow up of the intersection. The thin lines define the uncertainty about the relationship given by a certain value of the precession frequency, because we have an uncertainty about the precession frequency. We are assigning some uncertainty also to the conservation of angular momentum, and then the intersection of these two define an uncertainty ellipse, and we can calculate the uncertainties of these two. So we can keep getting the uncertainties. I really carp on this point of always having an idea of how well you know. It's not, I want to stress, it's not an absolute idea, right? But it really helps in making comparisons to other data and so on and so forth. Now, I showed you the picture for the equilibrium tide. So what does this tell us about the tides? And this is a very rich subject, in fact. A modeling tide. So here you see the M2 ocean tide is the main lunar semidiurnal tide that we see typically. And you can see the highs and the lows are shown in the two shades of the brown and the blue and so on. And you can see it's a very complex field. It's nothing like these idealized equilibrium tide that, however, captures something. But so what controls the dissipation of energy? And there are two interesting things to consider. One is that the dissipation of energy is high if the forcing frequency of the tide, which depends on the Earth's spin rate, right? How often does the tide come and go is how often you go under the moon, right? And the normal modes of the oceans. The normal modes of the ocean, I can give this very simple picture here to move the water in the ocean to one side and let it go, right? It will start to oscillate, right? And it's its own natural frequency. Now, if the forcing frequency of the tide and the normal mode of the ocean are close in frequency, then you get a resonance. Then the tide gets really big and the tidal dissipation, the same thing. So if you change the ocean configurations, right, as we have done many times during the Earth's history, then of course you change tidal dissipation. The other interesting point is that in the deep ocean, tidal dissipation is controlled by bottom topography. Okay, so irregularities like mid-ocean ridges, seamount chains, etc. This is from a paper by Peter Green. He's one of those who do a lot of these. And the high tidal dissipations is in the yellow colors. This is more or less the present ocean is actually at the last glacial maximum. But you can see that the parts of the ocean where there's high tidal dissipation is concentrated are that mid-ocean ridges, seamount chains, or all other sorts of irregularities at the bottom of the ocean. This makes it difficult to go back in time. So these are other simulations done 25 million years ago, 55, 116, 252. So this is like Permian. And the problem is that, of course, we don't know what the bottom of the ocean looked like at those times. So it gets very tricky to go back in time with these. At any rate, this paper comes from the Lasker group in 2022, and they made a model to figure out the history of lunar distance, length of day, and axial precession frequency. And so this is only calculated on the dissipation, in tidal dissipation in the geologic past. And it's based on past continent configurations in a very simple way, we'll show you in the next slide. And they obtain some good results in that the lunar recession, so it's constrained only by the lunar recession rate to match the present value. Now we know how fast the moon is moving away, because the Apollo missions left some reflectors on the moon, and we can shoot lasers. We know it goes away about 4.8 centimeters a year. Okay, it's kind of the plate tectonic rates, it's kind of how fast your nails grow, the moon is going to. And the other constraint that they wanted to obey was that the lunar distance would tend to zero at the age of the moon, 4.4 billion years ago. And so other models of the past tidal dissipation never managed to really do this just by modeling, okay? And in this paper, they say that they were not constrained by geological data, but the simulations fit them nonetheless. And in fact, these were the values for the Shamalin formation that we obtained in 2018, are these is that dot. And so their simulation goes very well through it. So this is where we can inform models of, so we are kind of the data constrained, if you will, to models of calculated models of tidal dissipation in the past. That's what this can do. I just want to show you how they did it, which is fascinating, which for us, for a geologist, you know, I come from geology, it's an amazing simplification. So for the period previous to 3.225 billion years, they assumed that there was only an ocean, there were no continents. Now we know the continents have grown, okay? So it's true that, you know, early in the Earth's history, they could be just ocean. But they didn't just appear, but because from 1 to 3.25 billion years, they have a hemispherical continent, essentially. So the Earth is two halves, right? One is continent, one is ocean. For the last billion of years, they actually used a reconstruction by these authors. This is the Earthbite group in Australia. And they have a reconstruction of continent. But because they are constrained to have this hemispherical ocean, because that gives them an analytical solution, all they do is to set the latitude of the center of these to the center of gravity of the continents. Okay, so this kind of works okay if you have a supercontinent, right? Like Pangaea, right? And you just smack a half Earth right there in the middle of Pangaea. But you know, most of the time things were pretty dispersed around. And so nonetheless, you know, their calculations give pretty sensible results. And as far as we can tell, they do match what we can get from the cycles in sediments. And again, the key here are these resonances, right? Depending on the Earth spin rate, which is modeled throughout, so the forcing frequency, there will be a resonance with this, which also depends on the position of the continent, right? So if you have an ocean that goes east-west like that, the resonance will be quite different than if you have a continent placed like that. And so here's just for illustration, I'm showing you the last 600 or so million years of these. And so, yeah, we're going to see Pangaea shortly assemble around 300 million years or so. There it is. Right, so there we have Pangaea, the Tethys here, and now Tethys will shrink, the Atlantic opens, and we finally come to the present. Okay, as a final thing for this, I wanted to, I'm going to show you something more after this, but I wanted to point out this paper, which is a really interesting idea, that the day length itself may have an effect on oxygenic photosynthesis. So they did this paper, they did quite a bit of modeling and observations of microbial mats that should be similar to what we had in the Proterozoic. And what they find is that as the sun rises, so during the night, of course, there's no photosynthesis. When the sun rises, the cyanobacteria start to work and start to do photosynthesis. But it takes a while before oxygen actually makes its way out. And I'm making this very simple. I mean, the paper is quite complicated. The point is that if days are short, right, shorter than 24 hours, so that illumination average is only 12 hours. But if that's shorter, there may be a large effect on the production of oxygen from the bacteria. So I wanted to show this as again, an astrobiology kind of thing, meaning that maybe we could also consider the rotation rate of external planets as one of the constraints. If the organisms are similar, there's a lot of questions here, about what kind of organisms existed at that time compared to the ones we find today and so on. But the resultant, that's the result. The resultant day-length-driven surplus organic carbon burial could have shaped the increase in atmospheric oxygen that occurred during the great oxidation event and the new proterozoic oxidation. So that's an interesting thing. So there's the geologic time scale. The Xiamalin data come from 1400 million years ago, so here in the Mesoproterozoic. But of course, now you would think, well, I mean, there's a lot more data, right? And so that's what I'm going to show you at the end. So we put together a lot of data that span the time interval in the blue shade. So between the sort of the end of the Proterozoic and about 55 million years ago, there's a lot of data in the literature where people have basically published astrochronology analysis. So we went back, we got those. That's the work of Eugene, who did this amazing amount of work while she was at Lamont only for a little more than a year. So we got data from 34 published studies in the interval between 650 and 55 million years ago. We used the same method in all records to make sure that the comparison was valid, and it's the method that I was showing you to you earlier, and we obtained the posterior distribution of the precession frequency. So the various estimates of the precession frequencies are shown here. The more intense colors are particularly significant data that really are significant for multiple cycles. And the dotted line is an interpolation. We use this method BCron, which is an interpolation method that makes sure that the precession frequency can never increase in this direction, which would be unphysical. Tidal dissipation can only make it go lower, it can never kick it up. You would need an external source of energy for that. And we compare it to what the Farhat et al. Paper, that's the blue line, was doing for this time interval now. That's a big zoom on that full, 4.5 billion year. So we're only looking at the end. But while there are some differences, here there's very few data, so we're not sure how terribly significant these are. Here there's also some differences here, but the general trends are quite similar. And so these were indeed obtained independently. Okay, so these are, we haven't done anything. The blue curve is here, but we haven't used it effectively to constrain this. Except in a very weak way, we just use the general trend here without these oscillations to define a prior range. And here you see the 95% interval of the prior range for K. And it's essentially there to avoid finding things that are completely unreasonable. That's all. But you can see that we can determine the values much better. So what do we use this for? Well, first of all, we can determine the periods of obliquity and climatic precession in the past much more accurately than we have been able to do so far. So people who, for example, have a data set at 250 million years, and they want to know what would be the precession frequency at that time, they can come here and get it. So you get different peaks in the spectra for precession frequency. There's a lump of them around the present value of 23,000 years. This is the period, the 1 over the frequency, and another one now 19. But if you go back, everything was going faster, right? So the frequency was higher, the periods were shorter, and you would have that. So this is useful for astrochronology. And then, of course, we can do the same thing we did for channeling and calculate lunar distance and length of day for all of those. And I'm going to use the lunar distance for a moment, because you can look up the relationship between, again, lunar distance, Earth spin rate, and the dissipation rate of tidal energy. So this comes from celestial mechanics, essentially, for a satellite. And so what you see here is the overall energy dissipation rate. Depends on the mass of Earth and the satellite, the moon. This is the moon's mean motion. So the rate at which it's going around its orbit. A, of course, is the semi-major axis, and omega is the Earth spin rate. So you can write this, you can write n in terms of A from Kepler's third law, so you eliminate that variable, so you're left with A and omega. The masses are not changing, hopefully, by much. And so you can look at this factor, Na times omega minus n, and you can use our result to say how much did it change. And even if you go back to 250 million years ago, it was only 8% greater than the present value. So it doesn't change by a whole lot. But the dA dt, right, the rate at which A is changing has changed quite a lot more, by more than a factor of 2. And so dA dt is dominating the signal effectively. So at the present is 3.8 centimeters a year. I think I said 4.8, it was right, 3.8. And again, this comes from laser lunar ranging. For this period between the present and about 150 million years ago, it was close to that. That's the slope of that purple line here. This is just done on the interpolation, right? But for this period, between 200 and 300 million years ago, it was much faster than the present. So there was a lot more tidal dissipation there. And then again, it becomes less than the present if you go back farther in time for the rest of the Phanerozoic, more or less between the beginning of the start of the Cambrian to the Carboniferous, roughly. But in this period here, it was a lot faster. And so this is puzzling, between 300 and 200 million years, because it was high when there was a Pangea supercontinent. But some of these studies that have looked at what happens when you have a supercontinent with a numerical tidal model, they generally say, no, tidal dissipation is low, because the ocean is so big that the resonance should not be excited. So it's a puzzle, okay? Because in fact, this is saying, no, it's the other way around. When there was a supercontinent, tidal dissipation was quite high. And there's no solution right now. It's more of a question that we're posing, but clearly these data are saying, no, I mean, that's what. So again, it's tempered from the fact that we don't really know, for example, what did the ocean floor look like between 300 and 200 million years ago. There's no ocean floor that old anyway, so much younger than that. And so maybe there was something there that really made tidal dissipation high. Maybe there's something else that we're missing. But it's a really interesting piece of information that I think this analysis can give. The tidal model of these authors, again, if you look at lunar distance, does show also a time of phi at roughly the same time, but not exactly the same time. So maybe there is something here, because there was that agreement. But again, right now it's just a problem. that we can highlight. So it's a original contribution, if you will. And so that does it. Essentially, what does geology tell astronomy in the broadest sense? Well, we can say something about the history of axial precession, of Earth-Moon distance, of length of day, and the consequences of the implications of that for tidal dissipation, for example. And that's just a summary, but I think we covered all of that. So thanks a lot for your attention. I'll be happy to answer questions.
All right, do we have any questions for Dr. Malinverno?
There's some back up there in the back.
That was a super enjoyable talk. I have two questions. One is about the idea of even getting a high R squared for these data because they're going to be noisy.
Yeah.
It seems like even a R square of 0.3 is a reasonable fit.
Oh, yeah, no, in those data that I'm showing you, the 34 ones, yeah, that's the kind of R squared that we get, and they're not very high.
Right.
But again, they've only vetted to be significant.
Okay, I think I guess that's the main thing I was taking away from there. And then second question is in Blue's paper, there's one posterior that doesn't go, the line doesn't go through at all. I'm wondering what that was. It's about like 500 MA or it's a bit older. Yes, like around 500 MA.
500, that one? That one?
Yeah.
No, we don't have a, again, these are, again, the ones that are shown there are plus minus 2 sigma, 95% bound. But remember, a 95% bound means you will be violated 5% of the time. So, you always have to keep that in mind. We have this notion that if you put out 95% bounds, it has to be there. Yeah, 19 times out of 20 will have to be there. But if one time out of 32 gets out, it's not necessarily that there's anything wrong. It's just statistically the way things are. Okay, yeah.
Thank you.
Yeah, sure.
Hi, thank you for your talk. I really enjoyed the opportunity to think about these questions and see how you're approaching them. I have two questions. The first is about the sedimentation rates that you're using. You arrive at an estimate of sedimentation rates that's actually quite narrow. I think you have something like 0.3 centimeters per 1,000 years. And we know that sedimentation rates are going to vary by orders of magnitude in the environments that you're studying. So of course, I understand that you're making simplifying assumptions, but could you talk a little bit about how you
you can have that. Now, most of the data that we look at are from deep water environments. So we don't think that sedimentation rates are that variable if you look more of a continental environment, say fluvial environment, then absolutely. Yeah. But most of the data we have are from either deep sea series or lakes. And remember, what we're really talking about is the average sedimentation rate over the length of record that we're looking at. And yeah, so if you were to go there and look at something like a sedimentation rate over a very short period, of course, it would be more variable than that. But if you think of those couplets, for example, of calcareous versus terregions and so on and so forth, the sedimentation rate for each of those could be quite different.
Yes.
Right? But as long as that cycle is expressed, yes, there will be a distortion in the sinusoidal shape, okay? But still, you will not change the period, right? And you're really looking at the average sedimentation rate for the whole thing. But the fact of using a constant sedimentation rate is obviously a limitation. We're forced to use relatively short records, because the longer you make it, the more likely you have a long-term change. And we are presently looking into how do we get out of that? And it's a bit of a balancing act. If I allow myself to change the sedimentation rate over a broad range, and then I can fit anything. Okay, then I can get astronomical cycles out of anything. Okay, I'm exaggerating, but you see the point. So you have to find the right point where you could say make a trend in sedimentation, account for a trend change in sedimentation rate with time, or maybe just a linear change, or maybe something a little more complex. But you want to do it so that you're not exposing yourself to the risk of basically varying the sedimentation rate to just make astronomical cycles. And so that's a little tricky. So of course, this of the constant is sort of the most, but clearly it's a limitation.
Yeah, so on these couplets, there are diagenetic processes that can result in more calcareous and less calcareous layers. How do you and right, that's a criticism of cyclostratigraphic study.
Yeah, it's been leveled, yeah.
I'm curious how you think about it and how that led to the selection of the 34 studies that feed into this record.
So the 34 studies are all published studies in reputable peer-reviewed literature, and they all made the case that there were astronomical cycles. Okay, you could have diagenetic cycles, but the point is that here what we're really looking at in this study is the relationship between cycles of eccentricity and cycles of precession, at least in some cases also cycles of obliquity. And so it stretches a bit the imagination to think that, you know, something like diagenetic processes would create cycles at exactly those frequencies. Not just one, not just a, you know.
But it depends on the smoothing that they're applying to their records as well.
Smoothing, what kind of?
There are a lot of, I mean, as you know, as you spoke about quite eloquently, there are ways that you can modify your data such that you get patterns and rhythmicity out of records. And so I'm just wondering, like, are these 34 studies that went into this paper, are they all radiometrically constrained? Are they all biostratigraphically constrained? Can you just speak a little bit to how you thought about distinguishing patterns in sedimentation, whether they're driven by obliquity or diagenetic processes from patterns, from meaningful external forcing?
Well, the way that we decide whether they're significant or not, I kind of went over that. We did not honestly look at diagenetic processes. We just looked at the data. In fact, we examined more than 34. I think the number is something like in the low 40s, 43, 44. And the difference is those that we found, that we analyzed, but we didn't find them significant enough. So we didn't just take everything, okay? We checked that they were significant to our criteria, but we did not do an analysis, separate analysis to say, oh, these are diagenetic cycles or not. We simply saw that there was these particular relationships. There's another component that I didn't talk about, which has to do with the modulation of precession by eccentricity that we also consider in this process. And so those are all things that we do not expect diagenetic cycles to do. There's a relationship between these different cycles that is peculiar to astronomical cycles.
All right, well, we're getting low on time, so do we have any questions on Zoom, Lisa? No? All right, let's hear one more round of applause for Dr. Malinverno.